Here we have simply support beam, and A support is a pin support, C is a roller support, and we have a point B, AB, the distance from A to B is L1, the distance from B to C is L2. So this beam is under uniform distributed load. The intensity of this load is W. And in this question, we also have some value for L1, L2, and the magnitude of the distributed load W, and we have the moment of inertia I, we have the Young's modulus E equal to 70 gigapascal. So the question is, what is the downwards vertical deflection at point B? So what is the deflection at the point B? So I would like to show you how to solve this deflection by using double integration method. So first of all, we need to solve the reaction force. So at support A is a pin support, we have two reaction force. So we have AY, we have AX. So two reaction force. And at roller support C, we have only one reaction force, CY. So if we write down the equation of equilibrium in horizontal directions, we find there is only one force, AX, okay? So this is only one horizontal force. That means this one, AX, must be equal to 0. Otherwise, we cannot satisfy the equation of equilibrium in x direction or in horizontal direction. So AX is equal to 0. And then look at these structures. So we have AY, CY, and we can see the AC is a symmetric structures, and the uniform distributed and the two reaction force. So this loading scenario is also symmetric. So by using symmetry principles, we can easily to derive that AY is equal to CY. So by using symmetry condition, and AY equal to CY is the half of the external vertical load. So the external vertical load is W times L1 plus L2. So W times L1 plus L2 is the vertical load, vertical distributed load. Because we know AY equal to CY, so then we know the AY and the CY is the half of the external load. So once we know the reaction force, and then we need to derive the internal bending moment, because if we want to use in double integration method, we need to apply a function is d square y dx square equal to m over ei. Okay, we need to know the internal bending moment. So if we want to know the internal bending moment, so we need to cut the beam, cut a section. Arbitrarily we cut a beam at section A to A. Okay, so then we look at this beam segment. So if we put the beam segment over here, so this beam segment, we have support A, we have cutting section A to A, and we have uniform distributed load. This is W, and we have a reaction force AY. AY is 1 over 2 W L1 plus L2. And at support at the section A to A, we have a bending moment. This bending moment is internal bending moment. So if we see the internal bending moment is M. So now if we write down the equation of equilibrium at this section A to A, so M A to A equal to 0. So this is the moment equation of equilibrium at section A to A. So if we say the positive direction is equal to clockwise, okay, so now let's look at the equation of the moment equation of equilibrium at section A to A. So first of all, the reaction force have a bending moment at support A. So we need to build up coordinate system y, x, and the support A to this section, say, is x. Okay. So once we know the distance from support A to this section, A to A, so we can write down the bending moment from the reaction force L1 plus L2 times the lever arm X. Because this bending moment, so this reaction force have bending moment at section A to A, so this bending moment direction is clockwise, so it's positive. And then we look at the distributed load. The W is the intensity or magnitude of this distributed load. So when we need to calculate the bending moment due to the distributed load, we need to first of all find out the resultant force of this distributed load. The resultant force is W times X. So this is resultant force of this uniform distributed load. And the position of this resultant force is at a half location. So the distance is X over 2. Okay? So we know this uniform distributed load have a bending moment Wx, the resultant force is Wx, and the distance or lever arm is X over 2. So because this bending moment direction is go to counterclockwise, so it's negative. So this is the bending moment due to this distributed load. And at last we have a internal bending moment M acting on these sections, and these bending moments go to counterclockwise direction, so it's negative M equal to 0. So this is the moment equation of equilibrium at section A to A. So once we have these equations, then we can derive the internal bending moment. So M equal to 1 over 2 W x squared. So this is, we have a negative over here, so then we plus 1 over 2 W L1 plus L2 x. So this equation is the internal bending moment equations. So once we know these equations, we can apply this expression into these functions. So we will have d squared y dx squared equal to 1 over 2 W x squared so we move EI, to the left hand side, so we'll have EI, put a EI over here. So to using double integration method, so first of all we apply the first integration on both sides of this equation. We will have EI dy over dx. We got 1 over 6 W x cubed plus 1 over 4 W L1 plus L2 x squared and plus C1. So this is first integration. And the second integration, we will have EIY equal to 24 W x fourth plus 1 over 12 W L1 plus L2 x cubed C1x plus C2. Okay, so we got two unknown constants, C1 and C2. So if we want to load the deflection of this, if we want to load deflection, we must estimate C1 and C2. So how to evaluate C1 and C2? We need to apply the boundary conditions. So the boundary condition So for boundary conditions, so because this is simply supported beam, at support A, the deflection equals 0, support C, deflection equals 0. So we can write down two boundary conditions. That means support A, x equals 0, y equals 0. This is support A. And the support C, x equal to L1 plus L2, y equals 0. So if we apply the first boundary condition, x equals 0, y equals 0, we will have C2 equal to 0. Okay, this is first, we have C2 equal to 0. Then we apply the second boundary condition, x equal to L1 plus L2 and y equal to 0. So if we apply this into the equation, we will have 1 over 24, because y equals 0, w L1 plus L2 force plus 1 over 12 w L1 plus L2 and L1 plus L2 cubed, and plus C1 times L1 plus L2, and C2 equal to 0, C2, so C2 equal to 0 and equal to EIY, y equal to 0, then is equal to 0. Okay, from these equations, we can evaluate C1. Okay, so the C1 will be, so we put C1 will be evaluate result of C1 is equal to W over 24 L1 plus L2 cubed. Okay, this is C1. So the C2 equal to 0, C1 we have this value, then we just plug in C1 and C2 back into this equation. Then we will have the deflection equation is y equal to 1 over EI. We just put EI to the right hand side of this equation. We will have 1 over 24 W x force plus 1 over 12 W L1 plus L2 cubed, and plus C1. So C1 is negative, so it's negative W over 24 L1 plus L2 cubed x. Okay, so this is the deflection equations. So after we have the equation of deflection showing here, so then we can evaluate the deflection at any point on the beam. So the question is, what is the downwards vertical deflection at point B? So point B is x equal to L1. L1 is equal to 335 millimeter here. So we just need to plug in x equal to 335 millimeter into this equation, then we can evaluate the deflection at the point B. So now I would like to put all these constants to here. So we know the E, we know the I, we know the W, we know the L1, L2. So now we just move the value E, the value E, and the value I, W, L1, L2. So move down to here. So we will have E equal to the 70 gigapascal. Okay, is equal to 70 times 10 to the 9th power Pascal. So and I equal to 6,480 millimeter to the 4th power, and equal to 6,080 times 10 to the minus 12 powers, because from this we convert the millimeter to meter. Okay, we know E, we know I, we know W is equal to 1/6 Newton per meter, L1 is equal to 335 millimeter, is equal to 0.335 meter. L2 is 455 millimeter, equal to 0.455 meter. So now we have everything in this, everything about the constant in this equation of deflection. Then we can evaluate the deflection at point B. Okay, point B is x equal to L1 equal to 0.335 meter. Okay, we have YB equal to 1 over EI. So 1 over EI. E is 70 times 10 to the 9th power. The I is 6480 times 10 negative 12. So this EI, then we go inside to the bracket 1 over 24. W is 160. X is equal to L1 is 0.335 to the 4th power. Second, 1 over 12. W 160 times L1 plus L2. So L1 plus L2. So we have 0.335 plus 0.455. Okay, so this is, then we times x cubed. So times x cubed. So when we just move the second term over here, so we just move the second term over here. 1 over 12, 160, L1, L2 times x cubed, 335 cubed. So this is second term, and the third term is showing here. So it's W 160 over 24 times L1 plus 0.455 cubed times x 0.335. Okay, this all the values we put into this equation of equilibrium. Then just using the calculator, we can just got result is 0.0174 meter. Okay, it's just 1.74 millimeter. It's because it's negative. So negative, that means the direction is going to downward. Okay, it's because our coordinate systems here, y positive is go to upward, so negative is go to downward. So it makes sense when we look at this distribution node. So now the result is showing here. The YB is 1.74 millimeter. So this is a solution to find out the deflection at point B.